Hello, everyone. I have lecture 6. And lecture 6. And this is my plan generally for this week. So we are going to continue talking about first-order circuits, have essentially one capacitor or inductor. And so we are going to do more examples of that. I'll also point out a couple of expressions, step response, pulse response, even impulse response, so that you're familiar with those if you see them later. And I'm hoping that this week, I don't know if we'll get there today, but if not, then on Thursday, hopefully we will start talking about second-order circuits. And, well, if a first-order circuit is one whose, the variable of interest is described by a first-order differential equation, a second-order circuit is one where the variable of interest is described by a second-order differential equation. Have you guys already seen second-order differential equations in your? Yes? OK, so you have just started that. So that's very good then. We'll be able to cover that more effectively. OK, so I want to just start by a quick review of a few concepts. A very important one being the time constant. Very often you see the letter tau used for. And by this we mean essentially the time scale that defines an exponential decay. Okay? And this is maybe at an abstract level, you can think of it like this. Imagine you have a signal, let's say some voltage, that starts with some value V naught and decays over time exponentially. So over time, well, let me maybe draw this bigger then. Here. Is this visible from there? Yeah. So you have something like this, an exponential decay, let's say starting from V naught. And so if we were to write this function, v of t, this starts with value V naught at t equals 0 and decays with a behavior like this. Okay? Now, I'm not referring to the answer for a particular circuit here. I'm just saying take a function in general that has such a behavior. The time constant tau is what you have in the denominator there in the argument of that exponential. And if you try to calculate after time tau what has happened to the signal, well, this is what you have. So in general, in this case, v of t is v naught e to the minus t over tau. And so if you, at time t equal tau, what you have is v of tau, which is v naught e to the minus tau over tau, which is v naught e to the minus 1, which is approximately, again, e to the minus 1 is 1 over 2.7-ish. So that's 0.36, actually closer to 0.37, 0.367. So you get approximately, let's say, 0.37 of v naught. So the time constant tau is the duration after which the function, the exponential function, has decayed to approximately 0.37 of its initial value, or 37% of its initial value. Okay. Now, there are very few things to memorize in this course, but this is one of the things to memorize. Okay. And it's not just for this course. This is something to know, what a time constant means, because it's not a concept you encounter only in circuits, but in essentially any branch of science and engineering. Okay. So now let's take another example. So by the way, if it has decayed to 37% of its initial value, it means the amount of decay has been 63% of the total, right? It has lost 63% of its initial value. Here's another example, because it's something that sometimes people make a mistake over. So let's call this example 1. Here's another one. Let's assume you have a signal like this. So this is, again, a signal V of t. In this case, might be a voltage, but you could have a similar behavior for a current. Let's say in this case, it actually starts from 0. Or let's even be more general. Let's say it starts from V1. OK, so this was value V1. I should put it on the other side. And then goes to V2. In an exponential manner. If this is an exponential behavior, by the way, can you take a minute and write down what this function, what the analytical form of this function should be, the function described by this? Can you do that on your own? Notice this is not an exponential growth, right? It's actually something that ends up saturating to a value V2, okay? So it's not an exponential growth. But there's an exponential behavior in there, in the analytical form. Okay, let's see. So first of all, for t less than 0, well, this signal V of t is simply V1. It's a constant, right? But it's after 0 that it starts growing and eventually reaches a final value V2. This could happen, for instance, in the charging behavior of a capacitor. Okay, so I'm trying to inspect and see what the form of this function is. First of all, it should be something that at t equals 0 gives me V1, right? Second, it should have some exponential dependence, but such that after infinite time, that exponential part has gone away, things have settled, and I've reached V2, right? Now, so you might expect, and I'm doing this just by inspection in real time here, okay? So this is not a particular method that I'm advocating. So you might expect that this function has something to do with V1 and something to do with V2, okay? And has something to do also with some sort of exponential decay, right? Now, something like this, e to the minus t over tau, does this grow with time or become smaller with time? Become smaller, right? So my function is growing with time. So what should I do to this so that it represents something that becomes larger with time? Put a minus sign in front of it, right? So we need something like this, basically. Okay. Now let's try something. Taking these into account, let's try to see if we can write this. So, and by the way, I know that the value of e to the minus t over tau at 0 is 1. What? Is 1, right? At 0, the exponential function itself is 1, right? So what if I had something like this? Let me see, and I'm trying. I really don't know if this is going to work. Let's see what this does. Okay, at t equals 0, the exponential is 1. And so I have v1 minus v2 plus v2. So that's v1. So that's good. At t equal infinity, it's what? The exponential has disappeared. And so this is e to the minus infinity, which is 0. So I just have v2. So that's also good. Before I wrote this, I also argued that we needed something that's actually making this grow with time. So we needed something with a negative sign, which is compatible with this, right? Because v1 minus v2 is a negative number. OK? Because v1 is smaller than v2. So this works. All right? So and again, I did this just by inspection, knowing that this was going to have an exponential form. Okay. This is just as an aside about how to think about these functions. So what you're seeing is the final value here, and the initial minus the final value multiplied by the exponential term. You might remember we defined this concept of initial value and final value last time. And so this kind of thing is very common to see. People will talk about the value, initial value. For instance, this could be called v of 0, right? Because it's v at time 0. And v2 could be called the voltage at time infinity. So again, this is just to be familiar with terminology. You might say this is v of 0, and this is v of infinity, the final value. Okay. It's just really notation and terminology that I want you guys to be exposed to. Okay. Anyway, so let's go back to the concept of time constant. So if I go after one time constant in this circuit, so let's say this is tau again on the time axis. What should this value be? That's the question. What value have I reached after a time tau? So that's one good answer. So let's write that down as a candidate. So what is v after time tau? So one possibility, you said approximately 0.67 v2. So that's one candidate. Sorry, 6.3. That's what you meant, right? 6.3. Yeah. Thank you. How about another candidate? Any other suggestions? So 0.37 V1 plus V1 plus V1. Any other candidate? OK, so you're saying 0.37 V2 plus V1. OK, so clicker time. You want to make another suggestion? Oh, we have one more suggestion. So that makes it better for clickers. OK, so the answers are getting bigger as we go down. That's good. All right, clicker time then. I think it's four options are good enough. So if you don't like any of these, click E. OK, very good. So the options suggested were not very popular. Let's see how who's right. So I kind of prefer to erase these to make room for our discussion. Yeah. Now let's see. Let's go back to the definition of time constant and how the exponential function works. So all you have is, or all you have to consider is the fact that it's really this part going from V1, V2 that defines that exponential. And it's inverted because of that negative factor in front of it. Now, a time constant means the time that it takes for this e to go from its initial value, which is 1, to just e to the minus 1, which is to 0.37 of its value, right? In other words, it's the time that it takes for this to lose 0.63 of its original value, right? So this segment that you see on the vertical axis should be 0.63 times this total difference, V2 minus V1, right? That's all. So it should be or V of tau should be approximately 0.67 of that difference, V2 minus V1, plus that V1 that you had on the axis. Right? Did I get that correctly? Yeah? 6.3, sorry, not 6.7, 6.3. Now, hopefully, that's what you would get if you put tau here. Is that what I would get if I put tau there in that equation? Has everyone verified that? Yeah? So you would get V1 minus V2 times 0.37, right? So that's 0.37 V1, which is what you have here, plus 0.63 V2, which is what you have there. Okay. What I really wanted to point out was this, that that's 0.63 of your V2 minus V1. Okay. This is something that very often people make a mistake about. And they kind of assume that if you hear about time constant, you should throw in 0.37. Well, 0.37 where is the question. So of course, if you have an equation like this, you can just put the time, tau, and get the answer. But the real insight comes from that you have to realize that the 0.37 in this case is here. Now, my drawing is not to scale, but this is the 0.37 of V2 minus V1. And the 0.63 is the lower portion there. Okay. So there's a couple of examples of time constants. Again, this number 0.37 or 0.63 is something really to memorize. And again, remember this concept of initial value and final value. You will hear about it quite frequently. I want to also formally define the concept of step response. It's something that we have seen in multiple examples. And then pulse response. So we have a source here, a resistor, a capacitor. And the source is described by a step function that jumps from 0 to V naught at t. I think we have done this exact problem before, so I don't want, or very similar to it. So I don't want to repeat the solution. You write a simple KVL, and you will get a differential equation and the answer. But the point that I want to bring to your attention is that your input is a step function. By the way, very, very often you will see this function designated as u of t. Stands for step function. Have you seen that in math somewhere, using the letter u to describe the step function? No? Yeah, it's common, u of t, a function of time that goes from 0 to 1, right? So this one, in this case, you could say v of s is v sub s of t is simply a v naught times u of t. And this is called unit step function. Which is defined like this. It's 0 for t less than 0 and 1 for t greater than 0. So it's just a step function, and our voltage, input voltage in this case, is a scaled version of that by value V naught. Okay. Now, the definition of step response is the response of the circuit to a step function. Okay. So step response is the response of the circuit to a step function excitation. Excitation or stimulation being the source that I'm providing to the circuit. And so it might be that I'm interested in the voltage of the resistor, in the voltage of the capacitor, or in the current in the circuit. So any of those variables could be of interest. And the answer for any of those variables would be the response to this step function or step response. Okay? Nothing special, and we've solved it before. So let's say if we thought about this current and this as V sub R and this as V sub C. Now we've repeated this KCL that tells us the current in the resistor and the capacitor. Those two currents are the same, so I will skip that step now and just use I for both. what would VC, the step response in this case, be that describes V sub C? Again, we've solved this or very similar before. So I'll just describe it qualitatively and write it down. Imagine this capacitor was not initially charged. So VC was 0 at time t equals 0. Okay? When the input jumps suddenly to V0 at that time, how does the voltage of the capacitor change at that point? It doesn't change. The capacitor does not like an abrupt change in the voltage, right? Because that would require infinite current. You've seen that before. So at that moment, the voltage of the capacitor is still 0. What will the value of the current be then? Vs over R. And Vs at that point has jumped to V0, right? So it's V0 over R. As time goes by, that current charges the capacitor up. And eventually, the current becomes smaller and smaller and smaller. And the capacitor gets charged to Vs fully in a behavior that has to do with an exponential decay. So for instance, if I wanted to plot Vc of t, if at time t equals 0, the capacitor was not charged, I would see something like this. This is what we just described. And you can write the equation, the KVL, KCLs, and solve it, and you get this. I think we did something very similar before. So from here, I also want to use this and define the concept of pulse response. Pulse response is the response of the circuit to an excitation or an input that's in the form of not just a step, but a pulse, which consists of 2 steps. You go up, stay there for some time, and then come back down. Okay. So my input, instead of just being that, will be like this. So consider the same circuit as above. But for the input, use this. So imagine at time 0, the voltage, the input voltage jumps to V0, stays there for a time capital T, and then drops back to 0 instantaneously. How would you expect this circuit to behave? So if we were to consider, again going back to the same circuit, if we were to consider the behavior of the capacitor voltage, Vc, what would we expect? Again, imagine this having been uncharged up until the action starts. Now we know that if we had the step function, excuse me, the voltage jumping to V0 and staying there, we just discussed the answer for that case. It would be this Vc shown right here in the middle. Well, if you have that pulse instead, initially, the circuit has no idea that after this step, things are eventually going to go down, right? At this point, the circuit has no idea. Up to the point capital T, the circuit behaves just as it did for the step. So it will grow like this. Had we not changed the input, the circuit would have kept going. Or in this case, V sub C of t would have kept going to saturate to the value V naught. But now, at this point t, all of a sudden, the input goes back to 0. What happens? It will now start discharging. Let's see what's exactly going on in the circuit. So if you look at the circuit, you'll see that when we impose V naught here, as we just discussed, there would be a current flowing in this direction from left to right, which charges the capacitor. And that's why your VC starts growing. After time capital T, all of a sudden you set this equal to 0. Now your KVL is back to VR plus VC being 0. And you solve that differential equation that comes out of that. And you will again see an RC type of behavior, where the initial condition is the voltage of the capacitor at that point, which we know does not change suddenly. And eventually, if you have no source here, so if this is 0, which means it has become a short circuit, 0 voltage drop, eventually, all the charge in this capacitor will dissipate. Now, if you have this capacitor, let's say, having reached, let's imagine some numbers. So imagine V naught was 5 volts, and after time t, this capacitor had charged up to 4.5 volts, right? Then now you set Vs to 0. This capacitor has 4.5 volts, which corresponds to some charge. And all it does is it will start discharging into this resistor. And that discharge is going to be described by an exponential decay. So this is what happens. Okay. Qualitatively, again, this is the kind of circuit that we've seen some examples of, and you've had several assignment problems on. So I don't want to go through writing the equations for it, but it's not any different from those examples. So this would be the pulse response of that circuit as far as the voltage of the capacitor is concerned. The capacitor voltage. So there is a question here as to whether the voltage of the capacitor has to persist for a small amount of time at time t. How small would that amount of time be? 0 in duration is the correct answer. In other words, the capacitor has no problem changing the trend in its voltage instantaneously. It doesn't like to change the value itself abruptly. And I hope my drawing here doesn't make it look like it's changing abruptly. It's really just that point. Okay? So before time t, this is actually a very good question, because again, this is the kind of thing that one could easily get confused about. Before time t, the capacitor voltage was growing, and it was looking at eventually saturating to V naught. At time t, the conditions changed, and now immediately it will reverse its trend. It will start decaying. But it has not changed its value instantaneously, right? So there is no sudden jump in its value. There is no discontinuity in its value. But changing the trend immediately is no problem at all. Okay. If I asked you to give me the current in the circuit, knowing this, what would you do? Having this graph, how would you calculate the current in the? Well, this is the voltage of the capacitor. So you wouldn't divide this by R, right? Because the capacitor voltage. So how is the voltage of the capacitor related to its current? It's derivative, slope, right? So just before t, if you take the slope of this curve, is it positive or negative? It's positive, right? Going up. So just before time t, the current I was positive, and the capacitor was charging. just after time t, what is the slope, positive or negative? Negative. The slope going, the tangent to this, right? If you take that slope, that's negative. So immediately after time t, the current has changed not only its value, but also its direction. And so your I becomes negative immediately. And so the capacitor starts discharging into the resistor. And a sudden change in the current of the capacitor is not a problem. Right? Can we qualitatively plot the current in the circuit? So if I wanted the function, the function I of t. Before 0, we had nothing, no stimulation. Everything was at 0. At time t equals 0, what is the current in the circuit? Let me go back to the circuit. So immediately after the voltage jumps to V0, what's the current? So one answer is 0. So I'm interested in the current I at time 0 plus. Yes. So at 0 plus, the voltage of the capacitor is still 0, right? Because it doesn't change suddenly. So what does KVL tell me here at 0 plus? What is the current? So it's Vs dropping over the resistor and the capacitor. If the capacitor voltage is 0, then the entire Vs drops over the resistor. So the current will be V0 over R. The capacitor at that moment has 0 volt across it, which is like a wire. And it can allow the passage of any current. But it's only at that moment. So I'm not a huge fan of using the term wire at that moment for this, you see. Because when we talk about steady state, an inductor being like a wire, that's for an extended period of time, and there is less chance of confusion. Here, it's really just at that moment that it has no voltage. So it could maybe lead to misunderstanding. So I'd rather just say, at that moment, the voltage is 0. OK. So at that moment, the voltage is 0, and the entire voltage drop is on R. And so the value of the current is V0 over R. And this current starts decaying exponentially as the capacitor charges up, right? And the equation for it is simply V0 minus that VC, and that's the voltage drop across the resistor. And that's going over the resistor. What happens at time t, capital T? How do things change at capital T? The current becomes negative, as we just argued, by the slope of Vc of t. Now, what is the value of the current going to be at that point? Let's see. Well, first of all, let's see what I need to be able to answer that question. So at t, we said that the source becomes 0 all of a sudden. So all I have now is the voltage of the capacitor dropping across the resistor. And that tells me the current. So I need the voltage of the capacitor at that point. It would be useful to maybe write the equation for this. So if we are describing that Vc of t, what is the formula for it? Well, first of all, for t less than 0, Vc of t was 0. Now, for t between 0 and capital T, What is VC of t? Again, by inspection. It's essentially the problem we just looked at without an initial value, right? So it's what we had up here, but except that in this case, V1 is 0, and V2 is V0. So it's V0 minus V0 e to the minus t over tau. That's going on until time capital T. So at that specific point, then, its value is simply this. That's VC at time t. Well, if you have VC at time t, all you have to do is write a KVL with the input being 0. So you have VC of t here and a resistor there. So the current will be in the other direction, that VC of t divided by R. So you're and in the other direction, so meaning negative. So at this point, this will be the value of the current. And then, from then on, the current will decay towards 0 eventually, when the capacitor is fully discharged. So you see there is this huge discontinuity in the current. And that's no problem at all. There is nothing in that circuit that would oppose a discontinuity in the current. The capacitor has no problem with that. The resistor has no problem with that. And it's just the fact that the pulse input to the circuit will require this response. That's all. I'd like to look at another example now. So again, example. So consider this circuit. Or let's say can you work a little bit on your own? So you're assuming that the circuit was sitting like you see, like that, for a very, very long time until t equal 1 second on the time axis. Okay? So we are interested in the voltage of the inductor as a function of time, for all time. Okay, let's solve this. And so maybe to help a little bit with also a little bit of review, given that many had difficulty with the previous example where we went a little faster maybe. Let's just write this down with all its detail. So first of all, t less than 1 second, we had a DC steady state for a long time. And well, the right half of the circuit was basically just this inductor in parallel with the resistor. Now, the inductor, for the inductor, voltage is proportional to the derivative of its current, right? And if you're in DC steady state, the time derivative of the current is 0, so the voltage is 0. So VL, which is L, so let's call this IL and this IR. DIL by dt is 0 in DC steady state, okay? And from that, you immediately, if you consider this KVL, and if you say this is V sub R, you have minus VR plus VL equals 0. So VR equals VL equals 0. And so from there, you conclude that I sub R, which is VR over R, is 0. Now, what does that say about the current of the inductor? Let's see what KCL says. At that node, for less than 1 second, you see this top wire is not connected anywhere. So you have minus IR minus IL equals 0. So IL happens to be minus IR happens to be 0. So there's a full solution of everything there. And of course, the current I naught is circulating in the resistor R1 on the left-hand side. There is a reason I put that resistor there, because if I had this current source with I naught not connected anywhere, where would its current go? It wouldn't be happy, right? So that's why I put that there, so that it can take that. And the voltage across R1 would be I naught R1, and that voltage also appears across the current source. Now, for t greater than 1 second, the circuit has changed, so the switch is the other way around. Let me draw that. This is open here, but closed on the other side. So all of a sudden, in the top branch here that I'm pointing at, going from no current in that branch to all of a sudden I naught. So you might say this is a step change in that branch, right? So again, I'm looking at a step response in this circuit. So all of a sudden, the current here is all I naught, because this is now open, and this is the closed switch here. So I have I naught going like this. And again, I have VR and VL, which are equal. And I have IR and IL. OK? So again, my KVL is the same as before and gives me VR equals VL. My KCL, on the other hand, has changed, because now I have I naught going in and still IR and IL leaving. So the sum of those two is I naught. Okay? So what do I do from here? Well, I have to rearrange things in the form that would give me a differential equation, hopefully first order, that has only one variable in it. So let's say if I am interested in VL, I can, for instance, write VR in the form of IR. Well, try on your own, or you already did try on your own, sorry. Yeah. So, so let's say from this one, I can say VL equals VR, which we know is R I sub R, which then from this KCL, I can write as R times I naught minus IL, which then I can write like this. So VL is R I naught minus R IL, and IL is what in the form in terms of VL? It's an inductor, so L. Oh, sorry. 1 over L. If I don't think I have written it there, so let's write it here. IL is, sorry, what am I doing? VL is L DIL by dt. So IL, in this case, if I'm looking at t greater than 1 second, is basically that integral going from t equals 1 second to whatever t I have, VL dt, plus whatever value of IL was at 1, right? The initial value. So I'm just replacing minus R times IL, which is IL of 1 plus this. And all you have to do now is to take the derivative of both sides to get dVL by dt equals the derivative of the constants goes away. So you're left with minus R over L VL. The derivative of the integral of VL dt is VL. And if you want to rearrange it in a more familiar form, and this is something that, again, we saw similar problems to before. So that gives you, again, an exponentially decaying function. Okay. Could you verify to make sure I haven't made a mistake? Yeah, is this correct? Is that, who has followed it and is correct? Give me assurance. Yeah? Correct? Well, follow it and come up with a more definitive answer. Okay, so if we want, so we solve for V from here, and again, your usual would be something T over tau plus B. Okay, so now you need the initial condition for this. At t equal 1 second. And in fact, if you want to be very rigorous, say 1 plus immediately after that switching action. Okay, so I should have put 1 plus here also. What is VL at 1 plus? Immediately after that switching action, what is the value of V sub L? Is it 0? What do we know about the inductor at that point? So, excuse me. Why is it that no current passes? Okay, very good. So what we know about the inductor is that it does not like a sudden change in the current, right? Because that would require an infinite voltage, which means before the switching, as we know, before the switching, there was no current. We had it somewhere up there. After the switching action, so at t equal 1 plus, the inductor still hasn't changed its current, doesn't like it. So the current of the inductor at t equals 1 plus is 0. So let's say this is a question mark, right? Now, we know that the current of the inductor at 1 plus equals the current of the inductor at 1 minus equals 0. What does that say about the rest of the circuit? We know that there is current I naught going through this branch, and it's being pushed over to the resistor and inductor, right? So if the inductor current is 0, all of that current has to go through the resistor, right? So KCL tells us that IR of, sorry, not 0, but 1 plus is I naught minus IL of 1 plus, but the latter happens to be 0. And so therefore, the voltage of the resistor at 1 plus is simply R I naught. But we know that the inductor and the resistor are sharing the same voltage because of a simple KVL up there. So VL at that point is simply the same. And so we have that initial condition. So we can say R I naught equals A at time minus 1 over tau plus B. By the way, what is tau? For this to be an answer to our differential equation, what is tau? It's not R times L, but it includes a combination of R and L. So in the case of a capacitor circuit, you saw that it was R times C, right? It was basically whatever you had in the denominator here. You had RC in the denominator, right? In this case, you have L over R in the denominator. Again, I think we saw this example before, so you can try on your own if you can't find it. Let's write it here. That's the time constant of a simple LR circuit. So I'll put it here also. If you can't find this on your own, come talk to me. But all you have to do is to try this form of VL of t in that differential equation. And you will see that for this to work, tau has to be equal to L over R. Well, there you go. So you have an equation that relates A and B. What else can we say? So we know that the inductor current at time t equal 1 is still 0, right? We said it doesn't like a sudden change. We have the value of the inductor voltage, R I naught at that point. What happens after some time passes? So the inductor current is initially 0. All the current is in the resistor, and there is a voltage drop of I naught R here. As time goes by, the inductor starts taking some of this current, right? And eventually the circuit will settle After a very long time, the circuit will settle. And nothing will change anymore, right? When things don't change anymore, if things are in DC steady state, what can we say about the inductor then? Acts like a wire. In other words, remember, V is L di by dt, right? So if things don't change, di by dt is 0. So the voltage of the inductor becomes 0. And so the inductor effectively becomes short-circuited. It does not mean that its current is also 0, right? Quite to the contrary. On this circuit, if the voltage of the inductor is 0 here, okay, what is the voltage of the resistor? Also 0. So what's the current of the resistor? 0. So where does all this current I naught go? Goes through the inductor, right? So after a long time, a DC steady state is reached again. Where VL, and in this case, call it VL of infinity after a long time, has become 0. Okay, so if you look at this equation up there, VL of t equals A e to the minus t over tau plus b. What does that tell us about A and B? If after infinite time that V should be 0. Well, if I put t equals infinity, what happens to the exponential term? Becomes 0. So it's A times 0 has no consequence. So the value after infinity is b. And we are saying b should be 0. Right? So A e to the minus infinity over tau plus b should be 0, which means A times 0 plus b should be 0, which means b should be 0. And so you have the answer now, VL of t, because if b is 0, then from equation 1, you have A equals R I naught e to the 1 over L over R, right? So from here, then VL of t is simply R I naught e to the power that times e to the minus t over tau, which is so it's again an exponential drop like we had before. It's just shifted, right? At time equal 1 instead of time equal 0 is where is the point where the switching action happens. So if you put t equal 1, this is 0. You have the voltage, sorry, exponential of 0, which is 1. You have the voltage R I naught. And if you put t equals infinity, it has decayed to 0. So here's just an example to show you another step response to maybe point out a few things, which is, first of all, you didn't need to have the source itself changing. I achieved this step behavior by using a switch separate to the source, right? An external switch. But I still made sure that my circuit didn't have any no-nos, such as a current source connected nowhere. So that's one thing. The other thing is a change does not necessarily happen at point 0 on the time axis. Here it was at at the point of 1 second in time. Now you might say, well, I can always shift my time reference to put that on 0, but only if you have one change. So if you have multiple changes at point 0 and 1 second and 5 seconds and so on, which could happen, right? You would have to basically solve the problem for each of those intervals and make sure that the transitions are taken care of properly by remembering that a capacitor does not like a sudden change in voltage, an inductor does not like a sudden change in current. Okay. And nothing changes to the mathematics of the problem or to the approach just because you have multiple changes in time at different points in time. If there's nothing you'd like to discuss, I want to maybe just introduce something a little fun in the next 10 minutes. You might say, strictly speaking, this is not part of our curriculum, but it's more about computation. Okay? Now, when I say it's not part of the curriculum, we are not required to do computational methods in this course, but it's very much on the topic. So I think it actually helps build good insight, especially if you like programming, which I hope many of you do. So a little bit of a numerical approach. To solving time-dependent circuits. Take the same example that we just discussed. Okay? Let's draw it in that more compact form of this IS. The same R and L. And assume that IS is a step function. So IS of t is I naught times a unit step function. And in this case, the unit step function is at 0, starts at 0. In the previous example, it started at 1 second. Doesn't matter. That would have been a shifted step function. What if I wanted to solve this problem numerically to see how things evolve? Okay. So let's go back to the same things, VL, IL, IR, VR. We just argued in the previous problem that right after the transition, which was at 1 second, but here is at 0, doesn't matter. Right after the transition, the inductor hadn't changed its current, was still 0. And so all the current went through the resistor, which gave us an initial voltage of I naught R. So like in the above example, in this case, VL at 0 plus is that. And we know in this case that it's going to decay exponentially. But what if we wanted to do it numerically? Now, in these first order equations, you have a simple analytical solution, so there's no real incentive to do it numerically. But imagine you had a more complex circuit, and you had something that even involved nonlinear elements, and you ended up with equations that have the third derivative and even nonlinearity and so on. So basically no analytical solution. In that case, you would want to do it numerically. And this is something that we do on a routine basis. Every time someone's designing a circuit these days, they do this kind of thing in a computer. So let's write the equation again. And I'll just repeat the equation from up here. No need to rederive it. dVL by dt plus so that's for t greater than 0 plus 1 over L by R VL equals 0. Okay? I want to solve this equation numerically by moving in small steps in time. So rather than using an analytical solution, I want to say my VL. Well, we know everything was 0 up to that point. At that point, VL jumped to Ri naught. This is my initial condition. So this is my VL of t. And from here on, I want to look at how this evolves and do so numerically. So I will discretize my time axis in small steps delta t. Sorry, this is too small maybe. It's a small step delta t. And of course, the smaller delta t, the better representation of a continuous problem you have with numerical discretization. All I have to do is to recall, keep in mind that this equation, what it really means is it is valid for all these times t, right? Although I'm not explicitly writing t all the time, but the equation is valid for all time t greater than 0. So I can also write it like this. At a given point in time, the derivative of this voltage happens to be proportional to its value. And if I want to solve this numerically, all I have to do is to discretize this derivation. So I will approximate the derivative by a simple difference. So the derivative at time t, I will say, is approximately equal to, what is the definition of derivative? It's the rate of change, right? So I take the difference in the value of the function between 2 points and divide it by the time that has that distinguishes the 2 points, right? So it's delta v by delta t in the limit, correct? So it's really delta VL by delta t at time t, approximately, which then would be, for instance, I could write it as this, VL of t plus delta t minus VL of t by delta t, right? So then my equation, let's call this equation star, becomes approximately VL of t plus delta t minus VL of t by delta t equals minus 1 over L by R VL of t. So you have gone from a differential equation to a difference equation. Now imagine if you knew the value of VL at some point in time, if you know VL of t, you have everything you need to calculate VL of t plus delta t, right? Because the rest is, delta t is something you chose. let's say you move in steps of 1 millisecond. So that's a constant. L and R are known values. So from here, you can rearrange things and say VL of t plus delta t is simply VL of t minus delta t over L by R VL of t. Is that correct? Yeah? Please verify. And so you can start moving in time. So having an initial value in this case VL of 0 plus, we can start moving in time in steps of delta t. So imagine delta t is 1 millisecond. So I know the value at 0. I plug it in here. I'll calculate the value at 1 millisecond. And then I'll put the value at 1 millisecond here. I'll calculate the value at 2 milliseconds, and so on and so forth. And I can track this behavior in time. This is called the method of finite differences. You turn the equation into a finite difference equation. And in particular, because we are working in time, finite difference time domain, FDTD, is known. So this is the method above is called. Give me two more minutes, please. Finite differences. In particular, in this case, because it's in time, finite difference time domain. Okay? Now you might not be very motivated to do this for this very simple circuit to which you know the analytical answer, but for more complex problems, numerical solution is the way to go. And in fact, I will give you some examples. I'll post some extra problems for practice later this week, other than the assignment. So these, you will not need to turn those in, but for your own practice. And there I will include an example of this in a circuit. And for those of you who are interested in coding, you can try to write a little program that will solve the circuit for you. So this is it for today. Thank you.